Hello students, this is Dr. Ravindra Munje and today we will talk about synchronous motor drive. In that we will see variable frequency control. So learning outcomes for today's session are, at the end of this session students will be able to appreciate the importance of synchronous motors in electrical drives. Students will be able to explain the reason of keeping V/F ratio constant, and also students will be able to differentiate true synchronous and self-control mode of variable frequency control. Now, synchronous motor runs at synchronous speed. Synchronous motors runs at synchronous speed or it remains standstill. Now synchronous speed is given by this formula, that is Ns is equal to 120 into F upon P, where Ns is a speed in RPM, F is frequency and P is number of poles. In this case, synchronous speed is directly proportional to the frequency, and as a result, synchronous motor speed can be controlled by varying the frequency. Now, in the past, these motors were used for constant speed applications because due to unavailability of the economical variable frequency sources, this method of speed control was not used in the past, and hence these motors were mainly used for constant speed applications. However, with the development of semiconductor devices, variable frequency sources such as inverter, cycloconverter allowed the use of synchronous motors in variable speed applications. Now for speed control operation of synchronous motor, it is operated with the constant V/F ratio below base speed. That is, for speed control below base speed, V/F ratio is maintained constant. However, this ratio is increased at low speed to compensate for the stator resistance drop with constant pullout torque. Whereas for speed control above base speed, motor is operated at rated voltage and variable frequency. Here, pullout torque decreases with increase in frequency. So the operation below base speed and operation above base speed are achieved with the help of this method. For the operation below base speed, this V/F ratio is maintained constant, and for the operation above base speed, this V is constant, whereas F is varied. V is a rated value in that case, but F is varied. So we get operation above base speed. Now we will see some terms related to pullout torque and pulling out of step. Now power produced by synchronous motor is given by Pm is equal to 3 times VE upon Xs into sine delta, where V is supply voltage, E is excitation EMF, X is stator reactance, and delta is a torque angle or power angle. So from this equation of the power, we get the expression of torque as Pm upon omega s, where omega s is a synchronous speed in radian per seconds, which will be equal to 3 into V into E upon omega s into Xs multiplied by sine delta. So for given value of supply voltage V, frequency F and excitation EMF E, torque will be maximum when we have the torque angle as 90 degree. And when we put torque angle as 90 degree in this expression, we get Tmax is equal to 3 times VE upon omega s into xs. Now this torque is called as the pull-out torque. This torque is called as the pull-out torque. As we have discussed in the earlier slide, for the speed control below base speed, V by F ratio is maintained constant, and however this ratio is increased at low speed to compensate for the stator resistance drop with constant pull-out torque. That means whatever the maximum torque that we get with V by F ratio as a constant below base speed, that is nothing but the pull-out torque, which is given by this expression. So this is nothing but pull-out torque. This Tmax is nothing but pull-out torque. Increase in the torque beyond this value. So if the torque is increased beyond this value, will cause motor to slow down and the synchronism is lost. Right? If the torque is increased beyond this value, motor will lose the synchronism, right? And that is nothing but the pulling out of step. That is nothing but pulling out of step. So we have seen what is pull-out torque and what is pulling out of the step. Pull-out torque is the maximum torque, and pulling out of the step means to go out of the synchronism. To go out of the synchronism, right? Then we will see why there is a need to keep this V by F ratio constant, or why V by F ratio is maintained below base speed to get speed control below base speed. Why this V by F ratio is maintained constant? So as we know that this supply voltage is proportional to product of the frequency and the flux. Supply voltage is proportional to the product of frequency and flux. If frequency is decreased without changing the supply voltage, what will happen? Flux will increase. If the frequency is decreased in this expression without changing supply voltage, flux will increase. As a result, motor will saturate. As a result, motor will saturate. Magnetizing current will increase, distorting the line current and voltage. Distorting the line voltage and current. Then because of that, core and stator copper losses increases and produces high pitch acoustic noise. Then the motor produces high pitch acoustic noise. On the other hand, if the flux is decreased beyond rated value, torque capabilities of motor will decrease. Torque capabilities of motor will decrease. Hence, V by F ratio is maintained constant. Hence, V by F ratio is maintained constant. Now, variable frequency control, whatever we have discussed, variable frequency control means keeping V by F ratio constant below base speed and changing frequency above base speed. So, variable frequency control may employ any of the two modes which are given below. That is true synchronous mode, and the other one is self-control mode. True synchronous mode and the other one is self-controlled mode. Now in the next part we will see what are these two modes. So what is true synchronous mode? Now in true synchronous mode, stator supply frequency is controlled from an independent oscillator. This Fs is stator supply frequency is controlled from the independent oscillator. Frequency from the initial value. Now this is a synchronous frequency at initial value, and this is the synchronous frequency at desired value. So frequency from initial value is changed to desired value gradually so that the difference between the synchronous speed, and the rotor speed is small, right? So Fs initial is changed to Fs desired slowly so that the difference between Ns and Nr is very small. And because of that, rotor speed or rotor tracks the synchronous speed. This allows rotor speed to track changes in the synchronous speed. When the desired synchronous speed is reached, motor pulls into the step. Motor pulls into the step means it goes into synchronism, right? It goes into synchronism after hunting oscillations, right? When the desired synchronous speed is reached, rotor pulls into step after hunting and oscillations. So this variable frequency control not only allows the speed control, but it can also be used for the smooth starting and regenerative braking, as long as the changes in the frequency are slow enough for rotor to track changes in the synchronous speed. As long as the changes in the frequency are slow enough for rotor to track changes in the synchronous speed. So that change is small. In that case only it is useful, right? So true synchronous mode is where F is controlled from the independent oscillator. Fs, synchronous frequency at initial value, is changed from synchronous frequency to desired value gradually, so that the difference ns minus nr is small, and because of that small difference nr can track ns. When the desired synchronous speed is reached, rotor pulls into step, so it goes into synchronism after hunting and oscillations. And variable frequency control not only allows this true synchronous method not only allows the speed control, but it can also be used for smooth starting and regenerative braking, as long as these changes are small. This is the true synchronous mode. Now we'll go for next method, that is self-controlled mode. Right now this is self-controlled mode. In this case, the stator supply frequency is changed using an inverter. Stator supply frequency is changed using an inverter whose SCR are fired in sequence using the information of the rotor position or stator voltage. Right? Stator supply frequency is changed using inverter whose SCRs are fired in sequence using information of rotor position or stator voltage. Right? Supply frequency, now this F, supply frequency is changed in proportion to rotor speed. Supply frequency is changed in proportional to rotor speed, so that rotating field produced by the stator always moves at the same speed as that of the rotor. Or rotor field. This ensures nr is equal to ns for all operating speed. Now if we compare the earlier method, true synchronous mode, and self-controlled mode, here you can see that in this self-controlled mode, ns is equal to nr for all operating speeds. ns and nr are same for all operating speed, whereas in the earlier case we change ns and then nr will track the ns. But here ns is equal to nr for all operating speed. Consequently, the rotor cannot pull out of this step, right? And when this is happening, when they are at the same speed, the rotor cannot pull out of this step, and hunting oscillations are eliminated. For such a application, motor may not require damper winding. So in this case damper winding is not required. Alternatively, sensors can be mounted, right? On the stator to track the rotor position. These are called rotor position sensors. The frequency of signal generated by these sensors is proportional to the rotor speed. Frequency of these signals generated by these sensors is proportional to the rotor speed, and hence the stator frequency can be made to track the frequency of these signals. Right? Stator supply frequency can be made, that is Fs can be made to track the frequency of these signals which are coming from the rotor position sensors. Fr is a frequency signal coming from the rotor position sensors. So this is self-controlled mode. Now So whatever we have discussed, we'll just go back and we'll see. So here we have seen what is the variable frequency control. Ns is given by 120 f by p. Ns is proportional to f. So frequency can be varied by changing f, right? In the past, these motors were used for constant application because of because there were no variable speed converters available. But after that, with the development of semiconductor devices like devices in inverters and cycloconverters, it is possible to have the variable speed applications, right? After that, by keeping V by F ratio constant, we can have speed control below base speed, and by changing frequency with rated voltage, speed control above base speed can also be achieved. Now after that, what is pull-out torque? That is the maximum torque when sine delta is equal to 1 or delta is equal to 90 degree. That is pull-out torque. And pulling out of the step means losing the synchronism. To go out of the synchronism, that is pulling out of the step. Then we have seen why V by F ratio is maintained constant. If V by F ratio is not maintained constant, if F is decrease, then flux will increase, and increase in the flux will cause the will increase the magnetizing current, and it will result in the losses, stator copper losses and core losses, and will produce high pitch acoustic noise. Whereas if frequencies increase, the flux will decrease beyond rated value and the torque capabilities of motor will decrease. Hence V by F ratio is maintained constant. Then there are two modes of variable frequency control: true synchronous mode and self-controlled mode. In that case, we will see true synchronous mode when F is controlled from independent oscillator. In this case, Fs initial is changed to Fs desired gradually, so that this change in the speed, that is Ns minus Nr, is small, so that Nr can track Ns. When the desired synchronous speed is reached, rotor pulls into step or goes into synchronism after hunting oscillations, and this is also used for smooth starting and regenerative braking. In the self-control mode, F is controlled using inverter, right? F, that is stator supply frequency change using inverter, whose SCR are fired in sequence using the information of rotor position or stator voltage. Then F is changed in proportion to Nr, so that rotating field produced by the stator always moves at the same speed as the rotor. Here we need to note down two differences. The first one is, in this self-control mode, Ns is equal to Nr for all operating speeds, whereas in case of the earlier method, true synchronous mode, Ns and Nr are not same. Nr tracks the Ns for change in the frequency, but here in the self-control mode they are same. And the other change is, in this method there is no hunting oscillations, whereas in the earlier method, true synchronous mode, there can be hunting oscillations. Now sensors can be mounted on the stator to track the rotor position, and these are called as the rotor position sensors, and because of that the stator supply frequency can be made to track the frequency of these signals. So whatever we have seen in this short session is importance of the synchronous motors in electrical drives, why there is a need to keep V by F ratio constant for below base speed operation, and what is the difference between true synchronous and self-control mode of variable frequency control of synchronous motor drive. These topics we have discussed in this session. Next session we will talk about self-controlled synchronous motor drive. Thank you very much.